In this video, I'll work through an example of a multiple linear regression model with 3 predictors. So here's the data down here. We have a response variable PIQ and then 3 predictor variables, brain, height, and weight. And I'm going to fit this multiple linear regression model here. So I select stat, regression, fit regression model. And I put PIQ in the response box, and then brain, height, and weight in the continuous predictors box. And then click OK. And then here are the results. So I'll just scroll down to where it says regression equation. So this is the estimated equation based on this model. yi equals beta 0 plus beta 1 x1, beta 2 x2 plus beta 3 x3 plus error. And this estimated equation is the fitted or predicted response, PIQ, is equal to beta b0, 111.4, plus b1 times brain, 2.060 times brain, minus 2.73, that's b2, times height, plus b3.001 times weight. So that's our estimated or fitted or predicted equation. So just a quick note on notation. This is our population model here with betas. And then if we substitute b's in here, we'll get our estimated model, and this changes y to y hat, and then there's no error term. So the estimated equation is y hat equals b0 plus b1 x1 plus b2 x2 plus b3 x3, and if we substitute in the numbers here, y hat is PIQ here, b0 111.4, b1 2.060, b2 minus 2.73, and b3 plus 0.001. Mean square error here, the sum of squared errors divided by n minus p. So we would find that in the analysis of variance table. So the sum of squared errors is in the error row, the sum of squares column. So 13,321.8, that's SSE. N minus P, so N is the sample size, which is 38 in this case. We have 38 observations. And P, so P is the number of beta parameters in the model, including the intercept. Okay, so we've got 3 predictors. So 3 beta parameters for each of the predictors, plus the intercept term. So P is 4. So N is 38, P is 4. 38 minus 4 is 34. So that's this number here. Error degrees of freedom, N minus P, 34. If I divide 13,321.8 by 34, I would get 391.82, and that's the mean squared error. And then if I take the square root of the mean squared error, I would get this number here, which is denoted S, and that's known as the regression standard error, or sometimes the residual standard error. And this is an estimate of the standard deviation of the errors in the model, or the residuals in the model. Okay, let's go back to the coefficients table. So these were the numbers in my regression equation. 111.4 is B0, 2.060, B1, B2 is minus 2.73, B3 is 0.001. What do these numbers mean? Let's look at the 2.060. Okay, this is how much we expect the response, PIQ, to change when we increase brain by 1 unit and keep height and weight fixed. Minus 2.73, to interpret that, we would say we expect PIQ to decrease by 2.73 if we were to increase height by 1 unit and keep brain and weight fixed. And then 0.001, to interpret that, we would say we expect PIQ to increase by 0.001 if we increase weight by 1 unit and keep brain and height fixed. And then finally, what does the intercept term mean? 111.4. Well, mathematically, we could say this is what we would expect PIQ to be if all of the predictors were 0. So if brain and height and weight were all 0, then we would expect PIQ to be 111.4. But if we look at our data, that's not very meaningful in practical terms, because to have a brain value and a height value and a weight value all equal to 0, it doesn't make any practical sense. Okay, so it has a mathematical interpretation, the 111.4, but it doesn't really have a practical interpretation in this example. Okay, so that's the interpretation of the model parameters. Let's go on to predicted values and residuals. And let's refit the model. I can quickly pull up the last dialog I used by clicking this button here. And then this time I'm going to hit storage and I'm going to click fits and residuals. And that's going to give me 2 new columns. So fits, these are the values of y hat, or the predicted or fitted values of PIQ. And then RESI, residual, these are the difference between the actual value of PIQ and the fitted value based on the model. Okay, so if I was to do 124 minus 103.522, I would get 20.4784. Okay, so predicted values and residuals. And I can draw a graph, a scatter plot, with the residuals on the vertical axis and the fitted values on the horizontal axis. And ideally, this should resemble a horizontal random band of points. Okay, which it pretty much does in this case. Don't get too carried away by these 2 points on the end. There's only 2 values up at this end, and so we can't really get too worked up about just 2 values in the data set. For the bulk of the data, we've got a nice random scattering of points forming a horizontal band. And we'll talk more about that in lesson 7 when we talk about residual analysis. Another plot we can draw is, so that last graph that we looked at, the scatter plot of residuals versus fits, that's to assess the linearity and the equal variance assumptions. To assess the normality assumption, sorry, we don't want to do a scatter plot, we want to do a normal probability plot. So if we do probability plot, okay, the default one is a normal probability plot. And ideally, the points would lie along that diagonal line there. And they pretty much do in this case. There's 1 point that's a little bit off up here, but again, it's just 1 point. So we're not going to get too worked up about 1 point. Okay, so normality is probably okay for this example. Anyway, as I say, we'll talk more about that in lesson 7. Okay, let's go on to the analysis of variance table. Okay, we looked at this earlier when we talked about the mean squared error. So this top row here for the regression, the degrees of freedom for regression is equal to p minus 1. Okay, so it's just the number of predictors in the model. And then the sum of squares, and then the mean square is the sum of squares divided by 3. I'm not going to worry too much about these individual rows here for each predictor. We'll talk about that in a later lesson as well. I'm going to skip to the error row. So we discussed this earlier. So this was n minus p. This is the sum of squared errors, and this is the mean squared error. If I was to divide the mean square for regression by the mean squared error, I would get this f value up here, 4.74. Okay, so that's mean square for regression divided by mean squared error. Okay, and we'll talk about what that f statistic means in a later lesson as well. And then we've got the total row for the analysis of variance table. So if you were to add the degrees of freedom, 3 plus 34, you'd get 37. You add the regression sum of squares to the error sum of squares, you'd get the total sum of squares. Okay, so we talked about S. Let's talk about R squared now. So R squared is the ratio of the regression sum of squares to the total sum of squares. So 5572.7 divided by 18894.6. As a percentage, that's 29.49%. So we could say that 29.49% of the variation in PIQ about its mean can be accounted for by the predictors in this multiple linear regression model. Adjusted R squared, we'll talk about this in a later lesson as well, but here's the formula for it. And so if we do that calculation for this example, we would get 23.27%. Okay, let's get back to the coefficients table and look at the t-value column. So let's look at 3.66. So that's the estimated coefficient for brain. So in other words, B1, 2.060. It has a standard error of 0.563. So if I divide the estimate by the standard error, I get the t-statistic. And then if I compare this t-statistic to a t-distribution with 34 degrees of freedom, n minus p degrees of freedom, then I would get a two-tailed p-value of 0.001. So that's for testing this pair of hypotheses here, beta 1 equals 0 versus beta 1 not equal to 0. This p-value is smaller than a significance level of 0.05, so we would reject this null hypothesis in favor of the alternative. So in other words, there's a linear association between that predictor, brain, and PIQ, accounting for height and weight, okay? Because we always have to think about the other predictors in the model when we do a hypothesis test using the t statistics in this coefficients table. Okay, so if we look at the next one, height, so there's a linear association between height and PIQ, adjusting for brain and weight, but there's the p-value for weight is 0.998. So it's not smaller than 0.05. So we would say there's no real evidence of a linear association between weight and PIQ, adjusting for brain and height. Okay, so each of those are individual t-tests for the predictors in the model. Testing becomes a little bit more complicated in multiple linear regression compared with simple linear regression because we have to think about multiple predictors being in the model. And so we'll talk about that more in lesson 6. Okay, so that's an example of a multiple linear regression model.